Hello, everybody. My name is Silas Richelson, and I'm going to talk about a high-dimensional Goldreich-Levin theorem. This is joint work with Parker Newton and Chase Wilson. The Goldreich-Levin theorem certainly needs no introduction. It's a fundamental result in cryptography, coding theory, Boolean learning theory, and so on. Perhaps an overstatement to suggest that it's everyone's favorite theorem, but it's certainly a fantastic result. One of my favorite theorems, definitely. The version of the theorem that I'm going to talk about, I'm going to call the prediction implies inversion lemma. It says that if you're given oracle access to a function, a Boolean function, which has good linear agreement, then you can efficiently recover the linear maps which agree with f, with your function. In cryptography, the first use of this was to prove that one-wayness implies pseudo-randomness, but it has tons of other uses. In coding theory, this was the first list decoding algorithm for the Hadamard code. Lots of other list decoding algorithms have followed. It gives the results in effective property testing. I'm bringing this up because this will come up later. The BLR test is a fundamental result in property testing, which says that if you have a Boolean function which passes a linearity test with good probability, then your function has to have good linear agreement. And if you combine this with the prediction implies inversion lemma of Goldreich-Levin, which says that if you have good linear agreement, then you can efficiently recover the linear maps, you get this sort of combination theorem, which says if you have a Boolean function that has passes a linearity test with good probability, then you can efficiently recover the linear maps, which explain the test passing success. You can generalize Goldreich-Levin in lots of different ways. You can look at the case of large modulus, where you look at functions over ZQ instead of Boolean functions. You can generalize to the case of group homomorphisms. You can generalize the degree of the agreement. So Tilsiani and Wolf look at Boolean functions which have good quadratic agreement, and they prove structural results there. In this work, we're going to generalize to the case of high-dimensional output. So we're going to look at functions which take m bits of input and have n bits of output, and we're going to prove Goldreich-Levin type theorems for these functions. So this is a more slightly more detailed statement of the prediction implies inversion lemma. The notable thing about this statement is this agreement 1/2 plus delta, and it gives kind of a dichotomy. And what I mean by that is, the theorem, the stated theorem here, the Goldreich-Levin theorem, says that if you have agreement that's 1/2 plus delta, then you can recover the linear map. Whereas if all you have is agreement 1/2, then you can't possibly recover any structural information about f, because a random function has linear agreement 1/2. And so there's somehow this sharp threshold which says that, okay, if the agreement is 1/2, then it's hopeless because there's no structure that you can impose. And if you have agreement that's any better than that, then Goldreich-Levin says you can efficiently recover the linear maps which you agree with. And so if we wanted to generalize a statement like this to the case of a function with high-dimensional output, one question to ask is, okay, suppose we have a function, and suppose there's some matrix A such that the probability that f agrees with A is at least epsilon. Can we efficiently recover A? This would be sort of the direct generalization of the Goldreich-Levin to the case of high-dimensional output. And the answer, actually, it's not so hard to answer this question. It depends on epsilon. If epsilon is greater than 1/2 plus delta, then prior work says, yes, you can recover the matrix A. This is just basically the same techniques as the original Goldreich-Levin. Whereas if epsilon is less than 1/2, then no, you cannot. So it appears that there's sort of a dichotomy here as well, where, okay, if you're greater than 1/2 plus delta, then yes, you can recover it. And if you're less than 1/2, then you're out of luck. So, okay, why are you out of luck if epsilon is less than 1/2? It's not immediately clear, but here's a counterexample. This function so here's a function f, which outputs a of x, except for the first coordinate of output, where it just outputs a random bit. So clearly, f of x is going to equal a of x with probability 1/2, because it's just whether or not you get the first bit correctly or not. However, f of x is going to equal a prime of x with probability 1/2 for any a prime that shares the second through nth rows with a. Okay, and there are 2 to the m such matrices. And so what that means is that it's hopeless to try to recover A, because A is but 1 in an exponential size family. And so you can't efficiently hope to recover A. So this is too bad, because it seems like sort of the Goldreich-Levin dichotomy extends up to here. And so either, you're in the case where prior work says you can recover A, or you cannot. However, I would argue this is a false dichotomy, because if we look a little bit closer at the original Goldreich-Levin dichotomy, the threshold of 1/2 made a lot of sense, because if you're at 1/2, then a random function, a random function has agreement 1/2. So 1/2 is clearly hopeless. Anything better than 1/2, Goldreich-Levin says, yes, you can recover the linear map. In the high dimensional case, a random function agrees with A times X with probability 2 to the negative n, not 1/2. And so, okay, prior work says you can recover the matrix A if you have agreement 1/2 plus delta. But a random function says it's going to be hopeless to recover any structure when the agreement is 2 to the negative n. And so there's a big gap that's left open. And a fair question is, okay, well, what if the linear agreement is greater than 2 to the negative n, but less than 1/2? What can we say in that case? Okay, and by the previous example, okay, we can't recover A. But what we show is that actually we can recover some A prime, which is sort of like morally just as good as A. And I'll explain what that means sort of more formally in a second. But the key point is that if we look at this counterexample, the exponential family of matrices which agree with this function all agree with this function for the same exact reason. Namely, it's because of the second through nth rows. And this function has no information about the first row of the matrix. And so sure, you get an exponential size family, namely any first row, and then anything that agrees with A in the second through nth rows. In particular, all of the matrices in this family agree with F for the same reason. And so it shouldn't be our goal to recover this entire family because it's repetitive. And essentially what we show is that we can recover some A prime in this family, maybe not necessarily A, but something in this family, which is it's going to be just as good as A. Okay, so here's a statement of the formal statement of the main theorem. I'll read it. It says, there's an efficient algorithm, which is if it's given oracle access to some function which takes m coordinates of input and n coordinates of output, and the formal theorem is proven over a general field, ZQ. Again, the proofs are more or less the same for that in the binary case, so we state it over the larger field. Anyway, so there's an efficient algorithm which gets oracle access to a function, and if there exists a matrix such that F has good agreement with that matrix, then with good probability, the algorithm is going to output some matrix A prime such that A prime has good agreement with F and A prime has good agreement with A. Okay, and so I underlined efficient because it sort of deserves more explanation. So efficient, so the runtime of our algorithm is exponential in log of 1 over epsilon, where the log is base q, log base q of 1 over epsilon. So this is only really efficient in the sense of polynomial time when epsilon is a constant power of q. So q to the minus, it's like 1 over q, a power of q. What this means is that our result is actually our result gets stronger as q gets bigger, with kind of the weakest version of our result being when q equals 2. Nevertheless, for the entire rest of the talk, I'm just going to talk about the case of q equals 2 because just for simplicity. Okay, but we, our result gives, but just to say again, our result gives a polynomial time algorithm when epsilon is 1 over a power of q. And so that's more likely to be the case when q is bigger. So Goldreich-Levin is often stated as kind of a list decoding algorithm where you're trying to recover the entire list of all the matrices. And there's an analogous way to formulate our lemma 2, our main theorem. And I'm not going to discuss it. You can kind of pause the video and read it and think about it if you want. I'll just mention that the the sort of connection, if the original Goldreich-Levin result is a list decoding result, then our main theorem is what's called an approximate list decoding result. And approximate list decoding is it's a standard model in coding theory. It's a natural generalization or natural relaxation, I guess, of list decoding, which allows for decoding even in the setting where the list is exponentially large. And there's a whole theory of these approximate list decodable codes with prior work, et cetera. And our result, in the same way that the original Goldreich-Levin theorem gave an effective property testing result in the one-dimensional case, our main theorem is going to give an application to effective property testing in the high-dimensional case. So if you start with a high-dimensional version of BLR, which would say that, okay, if you have some function, m bits of input, n bits of output, and it passes a linearity test with probability epsilon, then there exists some linear map such that f agrees with the linear map with probability epsilon prime. Statements of this type would be sort of like high-dimensional analogs of the BLR test. And there are theorems which give sort of relationships between epsilon prime and epsilon. The best is a conjecture. So sort of there's a break. Theorems of this type are much harder to prove than sort of the original BLR test. It's deeply kind of connected to additive combinatorics, and there's a breakthrough result of Sanders in additive combinatorics in 2012, which got a quasi-polynomial relationship between epsilon prime and epsilon. It's conjectured that epsilon prime depends polynomially on epsilon, and it's known to be equivalent to some version of the polynomial Freeman-Ruja conjecture in additive combinatorics. And anyway, sort of it's an area of very active work, and our Goldreich-Levin generalization would make these theorems and conjectures algorithmic. Okay, so for the rest of the talk, I'm going to talk about the algorithm and analysis. So okay, let's sort of try to understand what's going on. So this is us. We're trying to design an algorithm that recovers the linear map which agrees with f. So we have oracle access to f. We can feed it inputs. We get outputs. And we know that f has good agreement with some linear map. And our goal is to recover some other linear map a prime, which is sort of close to a. And sort of a related and I guess equivalent question is, you know, given an x, and so we feed the oracle an x, we get f of x as output, and we're trying to understand whether f of x is equal to a of x or not. And if we can answer this question, then we can sort of just recover a prime in a pretty easy-ish way. Basically, you just find a basis of x's which such that f of xi equals a of xi for all I, and that's going to let you recover a. And so I'm not going to talk about sort of explicitly how you recover a anymore. I'm just going to try to answer this question, or we're going to basically try to give a way to answer this question with good probability. So if we feed the oracle an x and we get an f of x back, how can we tell whether it equals a of x or not? All we can say for sure at the beginning is that f of x equals a of x holds with some probability, but we don't have a better idea than that. Okay, so let's sort of try to answer this question. Before continuing, we're going to need sort of like a tool, which I'm going to call a side quest, and it's this question. It's okay, so forget recovering the entire matrix A. Can we recover just a row of A, like the first row of A? And it turns out that this is something we can make progress on just using the original Goldreich-Levin theorem. Basically, if you just look at the first coordinate function of f, if it has agreement 1/2 plus delta with like the first row of A, then okay, you could use the one-dimensional Goldreich-Levin theorem to recover A with good probability. So sort of more specifically, we have some high-dimensional function. We want to know if we can recover the first row of the matrix that it agrees with. And we observe that, okay, yeah, we could use original Goldreich-Levin if the probability of agreement was 1/2 plus delta. Unfortunately, linear agreement epsilon does not promise that we're going to have agreement 1/2 plus delta with the first row. It's pretty easy to build some pathological functions which have agreement epsilon with the first row. However, it's not, maybe we can't recover the first row, but we will be able to recover some linear combination of the rows of A. So sort of more specifically, we will be able to recover some row vector of the form Z times A for some row vector Z. And the reason for this is that somehow if you like average over all possible row vectors Z, then the expected agreement with basically the expected agreement of the function Z times f of x with Z times A of x is going to be bigger than 1/2. So we are actually in this 1/2 plus delta regime, namely 1/2 plus epsilon over 2 on average. And so what that suggests is that, okay, if we drew a random row vector, well, then with probability about epsilon, we'll sort of be in this, we'll have agreement 1/2 plus epsilon over 4. And so then if we run the Goldreich-Levin theorem, the original one-dimensional Goldreich-Levin theorem on the resulting like one-dimensional function, which sends x to Z interproducted with f of x, then with probability about epsilon squared, we'll recover the row vector Z times A. Okay, so sort of to summarize, we're able to recover a row of A, namely we're able to recover a pair, which is Z and then Z times A. So you can think of that as like, you can recover one linear combination of the rows of A with probability like roughly epsilon cubed. Okay, so that's at the end of our side quest. Back to our original goal, we wanted to recover some matrix A prime, which is close to A, and we have this new ability, which is we can recover a single row of A with probability epsilon cubed. So naively, this new ability can kind of already solve this problem. You just do it n times. So you say, okay, let's use our ability to recover Z1 times A through Zn times A for some basis Z1 through Zn. That would let us recover A. And, okay, we're going to take so that's great, except we have to take a probability hit of epsilon to the n. And that's way too high or way too small for us to be happy. We want to do way better than that. The problem is basically we're recovering one row of A with like non-negligible probabilities. So you can't put them all together n times because that's going to basically just decay exponentially. Okay, so let's go back to the question that we're starting with and try to figure out a better way to use our new tool to answer it. So okay, so again, we're trying to figure out whether f of x equals a of x, and again, we only know, all we can say at the beginning is that f of x equals ax holds with probability epsilon. However, let's run sort of let's run the algorithm from our side quest. Let's recover some row of A, namely some pair Z times A. And now, if we send x to the oracle for f and we receive f of x, we only have to wonder whether f of x equals a of x, given that like when sort of the one linear combination that we know holds. Okay, so basically f of x can't possibly equal a times x if Z interproducted f of x is not equal to Z interproduct ax. Okay, so basically, if we know one row of A, then we get basically one hint about whether f of x equals a of x or not. Okay, and so the probability now that we're able to answer this question of whether f of x equals a of x or not is going to be this sort of conditional probability, which is epsilon over the probability that the row that we have condition is satisfied. So it's going to be epsilon divided by the probability that Z times f of x equals Z times a of x. And this is going to be progress if the denominator here is like much less than 1. In particular, this probability is going to be bigger than epsilon. So we will have made progress. So somehow like recovering one row of A will have allowed us to answer this question more effectively. So this suggests the following greedy algorithm, which is going to be an improvement on the sort of just apply the new tool n times. Okay, so initialize a set S to be everything, and then do the main loop t times, where t is some number we'll pick later, where you recover a row of A using the tool that we have, and then you update S to basically remove from S all of the x's which don't satisfy the linear relation that we picked. Okay, so replace x with S intersected with the x's that satisfy the linear relation you found. And then at the end, okay, just output the set S. And as far as how to answer this question, I wonder if f of x equals a of x. Let's use membership in S as a proxy for for f of x equals a of x. Okay, so let's sort of look visually at what that algorithm is suggesting that we do. So in this picture, the yellow is the entire domain 0, 1 to the m. This blue is it's the set of x's where the function, that's supposed to be an f, the function f agrees with a of x. So this is basically the set that we're looking for. If we can find the set, then we can find a. And s, our set up here, is initialized to the entire thing. And as we sort of run the main loop over and over, we're going to shrink s. We're going to basically remove from s all of the x's which don't satisfy the linear relation that we recovered. Okay, so after we run it one time, maybe s is looking like this. After 2 times, it's getting smaller. After 3 times, and eventually, our hope is that basically s is equal to or like only slightly bigger than this blue set that we're looking for. Namely, we're hoping that sort of the probability that f of x equals a of x, given that x is in s, is roughly equal to 1. This would say that membership in S is indeed a good proxy for f of x equaling a of x. Okay, so to analyze this formally, you have to define this probability potential P. It's the probability that f of x equals a of x, given that x is in S. You notice that, okay, P equals epsilon when you initialize the algorithm. We need P to be very close to 1 at the output. And so the crux is basically showing that P is going to increase each time we go through the main loop, and understanding like how much P is going to increase. What we're hoping to get is that sort of each time you run the main loop, the new P that you get, notice that P depends on S. So after you update S, you have a new version of P. So the hope is that the new P is going to be a constant multiplicative factor bigger than the old P. And this is going to let us set T be equaling log of 1 over epsilon. And that's going to basically, that is what our algorithm is going to get. And that's going to give us the results in the theorem. So let's look at sort of what type of progress we can hope to expect here. So the key quantities are this P, that's what I defined last time. And I'm defining Q of Z now. It's equal to, it's a function of Z, and Q of Z is equal to the probability that Z times f of x equals Z times a of x, given that x is in S. And Z is going to be kind of an important quantity for the computations that we're about to do. Okay, so the main loop does 3 things. It draws a random Z, then it uses Goldreich-Levin to recover Z times A, and then it updates S. So we have basically 2 steps to analyze, the second and third. The first one is, we're picking Z randomly. So the correctness of the original Goldreich-Levin says that if Q of Z is bigger than 1/2 plus delta, or 1/2 is epsilon over 4, then Z times A is going to be recovered with probability roughly epsilon squared. The key computation for the third part is that you can actually compute the new P is going to equal the old P divided by Q of Z, where Q of Z is this quantity over here. In particular, if we can bound Q of Z away from 1, then you're going to get that constant multiplicative increase that we want. Okay, so sort of the 2 different non-trivial steps of this require 2 bounds on Q. You need a lower bound to say that, okay, the Goldreich-Levin theorem works, and you need an upper bound to say that we get that nice constant multiplicative progress. Okay, and so the claim is that if the probability that you have both a lower and an upper bound on Q of Z is not too small, then you're going to make that constant multiplicative progress with good probability. Okay, and this basically is going to, so this is, I would say, the analysis of 1 step of the main loop, and just by iteratively applying this over and over, you'll get the analysis of the full algorithm. Okay, so this condition is an important one. It allows us to make progress, and so let's give it a name. Let's call it the Goldreich-Levin progress condition, or GLPC. And the claim that we just stated is that if the GLPC holds, then we get that nice multiplicative progress with good probability. So the question is, does the GLPC always hold? Okay, and if it does, then we're done. Unfortunately, it doesn't. There's a counterexample. It's the same example that we saw in the intro. It's this function that agrees with A on the rows 2 through n and outputs a random bit on the first row. We already noted that P in this case equals 1/2. Remember that the Goldreich-Levin progress condition is this, I'm just restating it here. And you can compute that Q of Z, which is the probability that Z times f of x equals Z times a of x, is either going to be 1 or 1/2, depending on whether the first bit of Z is 0 or 1. Clearly, if the first bit of Z is 1, then you're going to multiply by a random bit. So the inner product is going to equal with probability 1/2. Okay, so in this case, this clearly does not satisfy the Goldreich-Levin progress condition because you're either at 1/2, which is below the bound, or you're at 1, which is above the bound. And the Goldreich-Levin progress condition requires you to be sort of not too close to 1/2, but also not too close to 1 with some good probability. And unfortunately, this is like always either equal 1/2 or 1. And so basically, this is a problem function for our algorithm. The algorithm is not going to make progress when the Goldreich-Levin progress condition does not hold. So the sort of basic greedy algorithm that we wrote down is not going to cut it. And so this is the last. This is basically the missing key, the key missing claim to our algorithm. So this is basically a claim that lets you make progress even when the Goldreich-Levin progress condition does not hold. And it says that, okay, if you have some function where the Goldreich-Levin progress condition does not hold, then there exists some non-zero w such that the probability that f of x is in the span of w is in a of x plus the span of w is that nice constant multiplicative factor times the probability that f of x equals a of x. Basically what we're saying is we can kind of loosen what we mean by f of x equals a of x. We're saying, okay, we don't care about f of x equals a of x. We're going to allow f of x to be in a of x plus the span of a one-dimensional vector w. And then we're going to get that nice constant multiplicative increase. So notice for the counterexample function, the probability that f of x equals ax was 1/2, but the probability that f of x is in ax plus the span of the first unit vector is equal to 1. Right? Because it's equal to a of x plus some random first coordinate. Okay, and so you get that. So if w, so for this function, w equals u1, the first unit vector, is going to satisfy this. So the proof is by Fourier analysis on the function q. I will leave the proof written here, but I will. So you can pause the video here and look at the proof. This is like a pretty fair high level overview of the proof. And the last thing I want to say is that sort of like, so how does this sort of fit in to give us a full algorithm? The answer is, so this is how our ultimate algorithm is going to work. It's similar to what we had. We still have this blue set that we're looking for. We still initialize S, this yellow set, to be everything in the domain. And we also initialize this vector space W to 0. And basically, we're going to step through the main loop, and every time we're going to check whether or not the Goldreich-Levin progress condition holds. If it holds, great. We do the thing where we run the one-dimensional Goldreich-Levin theorem, we recover one linear combination, we shrink S, as we saw. Okay, so if the Goldreich-Levin progress condition holds, we shrink S. If the Goldreich-Levin progress condition does not hold, then we increase W. We add one dimension to W, which is going to make the blue set bigger. Okay, and then we say, oh, maybe we keep going. Goldreich-Levin progress condition does not hold. Okay, make the blue set bigger. Now it does hold. Okay, shrink S. Now it does not hold. Okay, let's increase blue, and you get the idea. The hope is that sort of, what we can show is that eventually, x is going to be a very good proxy for f of x being equal to a of x plus something in the low-dimensional vector space W. And somehow this is going to be just as good enough. This is going to be good enough for us to recover A because W is going to have it is a low-dimensional vector space. All right, so that's a summary of our algorithm, and that's it. Thank you very much.